Welcome to the Explainer. All right, we're going to talk about a word that we hear all the time, but it's often, really misunderstood. That word is radiation. We're going to break down what it is, where it's coming from, and what you really need to know about it.
So let's kick things off with a little game. Just look at this banana. We all eat them, right? But here's the question. Is it radioactive? What do you think?
Okay, how about this one? The U.S. Capitol building. It's this massive, iconic landmark built mostly out of granite. So, is it giving off radiation?
Believe it or not, the answer to both is a big, fat yes. Bananas are full of potassium, and a tiny bit of that potassium is naturally radioactive. And all that granite in the Capitol, same story. It contains naturally occurring radioactive elements. Now, don't panic. This isn't dangerous. It just highlights a really important fact about the world we live in.
Okay, first things first, let's get one thing straight. Radiation isn't some rare thing that only happens in labs or power plants. It is a constant, totally natural part of our environment. It's been here since the Earth was formed.
So where is all this radiation coming from? Well, it's basically a mix. You've got what's called natural background radiation. That stuff streaming down from space as cosmic rays, coming up from the soil and rocks beneath our feet, and yep, even from inside our own bodies. And then you have the man-made sources, like the X-rays you get at the doctor's office, or even tiny amounts from stuff like smoke detectors.
So how does that balance out, natural versus man-made? This is where it gets really surprising for a lot of people. For the average person here in the US, a staggering 82% of your yearly radiation dose comes from completely natural sources. That's right, the vast majority of it is just part of being alive on planet Earth.
Okay. Next up, it's super important to understand that radiation is a huge umbrella term. It's not just one thing. It's actually a massive spectrum of energy.
And here it is, the electromagnetic spectrum. Way over on the left, you've got these really long, low-energy waves, like the radio waves to play music in your car. As you move to the right, the waves get shorter and they pack more of a punch. You go through microwaves, infrared, the visible light our eyes can see, then ultraviolet, and all the way up to the really high-energy stuff like X-rays and gamma rays.
So here's the key takeaway. The amount of energy a wave has is what determines how it's going to affect stuff, especially our bodies. Not all radiation is the same, not by a long shot.
And that energy difference brings us to probably the single most important idea for understanding radiation risk. I like to call it the ionizing divide. This is the real line in the sand that separates different kinds of radiation.
So what in the world is ionization? Well, it's what happens when a wave or a particle comes in with so much energy that it literally slams into an atom and knocks an electron right out of its orbit. When that happens, it can break chemical bonds, and that's the mechanism that can potentially damage a cell's DNA. And you can see that divide right here. Over on the left, you have non-ionizing radiation. Think visible light, microwaves, radio waves. They just don't have enough juice to knock out electrons. But on the right, you have ionizing radiation, like X-rays and gamma rays. They do have that power, and that is the fundamental difference when we talk about health risks.
All right, so let's zoom in on that ionizing radiation, the stuff with enough punch to knock electrons around. When a radioactive material breaks down, it usually gives off one of three main types. Let's meet the heavyweights, alpha, beta, and gamma.
This chart really shows how different these three are. Alpha particles, they're big and heavy, with a strong charge. That means they have a ton of ionization power, but they can't travel far at all. A single sheet of paper can stop them. Beta particles, those are basically just high-speed electrons. And then you have gamma rays, which are pure energy. They have no mass, no charge, and that makes them incredibly hard to stop.
If that table was a bit much, here's a super simple way to think about it. An alpha particle? That's like a heavy bowling ball. It does a lot of damage right where it hits, but it's really easy to stop. A beta particle is like a much faster, lighter baseball. It goes a bit further. And a gamma ray, that's like a beam of light. It just zips right through most things.
So if we're surrounded by this stuff all the time, and some of it is powerful enough to ionize our atoms, how do we even begin to measure the risk? Well, it all comes down to three things: dose, context, and protection.
Let's set a baseline. When you add up all the sources, the average person in the United States gets a dose of about 0.36 rem per year. Now, a rem is just the unit we use to measure the biological effect of radiation. So think of that number, 0.36 rem, as our normal, everyday exposure.
Now, to put that in perspective, regulators like the U.S. Nuclear Regulatory Commission have set a safety limit for the general public. That limit is 0.1 rem per year, and that's on top of the natural background radiation we already get. It's a pretty conservative limit designed to keep everybody safe.
Now look at this. The annual limit for trained professionals, people who work with radiation for a living, is way higher. It's 5 rem. This just shows that acceptable dose levels are carefully managed. It all depends on the context, the person's training, and balancing the benefits of the work they're doing.
So, what's the actual risk here? Well, the scientific consensus, like you see here from the NRC, is that ionizing radiation is a weak carcinogen. What that means is, while any dose technically has some tiny theoretical risk, small exposures are really unlikely to cause cancer. In fact, our bodies are amazing. We have these biological repair kits, like DNA repair enzymes, that are constantly fixing this kind of low-level damage.
And all of this leaves us with a pretty critical question. We know radiation is a natural part of our world. We also know it's an absolutely essential tool in modern medicine that saves countless lives. But we also know it's not entirely risk-free. So the big challenge for us is always going to be this. How do we best balance the huge rewards of using this powerful force against its inherent risks? That's definitely something worth thinking about.